Good afternoon, everyone. It is my privilege and my great pleasure to introduce the next plenary speaker, Professor Laura DeMarco from the University of Harvard. Laura graduated from Harvard under the supervision of Kurt McMullen and went on to become a world leader in the field of complex dynamics, arithmetic dynamics, to which she has made several fundamental contributions. As a consequence, she was also the recipient of many academic distinctions. I will not go through the list and just mention two. Laura is a member of the National Academy of Sciences of the United States, and perhaps even more importantly, she was a plenary speaker at the 2018 International Congress of Mathematicians here in Rio. We are very happy that she accepted to come back and give this lecture to us today on rigidity, uniformity, and the Mandelbrot set. Laura, please.
Thank you very much, and thank you for the introduction and the invitation. I told Marcelo yesterday that I came first to a Colóquio Brasileiro in 1999, so it's really an honor to come back now as a speaker. I was a student at the time, and my advisor that he mentioned, McMullen, was speaking at that particular colloquial. And here I am, so thank you. It's really an honor. So I want to talk about the Mandelbrot set. This is one of the most famous fractal images, maybe the most famous fractal image, at least among the images that are considered central to mathematical research today, that play a very important role in current research. And so what I wanted to do with this lecture was to, well, if you don't know the definition, don't worry. I will give you the definition of the Mandelbrot set. I'll tell you what it is. I want to say a few words, a little bit about why we consider it important, why we've been studying it actively for more than 40 years. And then in the last part of the talk, I want to say some examples of what we're doing with it now, and specifically what I'm interested in and how it's connected to many different areas, and surprisingly also to algebra and number theory, and not just analysis and geometry, but also algebra. So the Mandelbrot set. By the way, of course, if you go to the internet and Google the Mandelbrot set, you will see many, many, many beautiful images, more beautiful than the ones that I've produced here for this lecture. I've stolen a few of them from the internet just so you see. I'm sure these are familiar to many of you, these types of pictures. But okay, so what is the Mandelbrot set? The most basic thing you need to know, it's a subset of the complex plane. So here I've drawn for you the real and imaginary axes. 0 there in the center. And to give you a sense of scale, I've put 1 and I on the image. In fact, so the Mandelbrot set itself is what's depicted in black. 1 is not in the Mandelbrot set. I is in the set. Okay, so what is it? So for each complex number C, we associate to it some particular sequence of numbers generated recursively, iteratively. And the recursion is very simple. Figure this out. There we go. Okay, so I've indicated it here. For each complex number C, you start with 0, and then you recursively build this sequence by squaring and adding the number C. So this gives you this infinite sequence of complex numbers. And just for terminology, I'll mention, we'll call this the orbit of the starting point. The language orbit, because this recursion is an example of a dynamical system, the subject of which has its history and planetary motion and others. So orbit comes from the idea of motion of a point. Okay, so this is called the orbit. And the Mandelbrot set, here is a definition. Very, very simple. The set of complex numbers C for which this orbit of points never leaves a ball of radius 2. Okay? That these numbers are always less than or equal to 2 in absolute value. Very, very simple definition. But not very illuminating definition, and it's not clear from that definition why we would draw this picture and why we would care and why we're still studying it 40 plus years later. So one very quickly, upon looking into it more carefully, sees that this object can be defined in many different and equivalent ways. There are a lot of reasons why this set has become important. The first observation I want to make is that the number 2 here is not important. The real point here is that it corresponds to the set of C's for which the orbit, that sequence that you get under the recursion, is bounded. Now, 2 happens to be the smallest radius you can choose to just have an easy yes or no for any value of C. But we could have chosen 10, or for each individual C, you could just check whether or not your sequence of numbers is getting big, whatever big should mean. But what is important in this image is that we're starting with 0. Okay, so the bound of 2 doesn't matter, but the fact that I'm starting with 0 is important. And what's special about 0 is that 0 is the unique critical point of this polynomial function that defines the recursion. 0 is where the derivative vanishes, and it's the only point where the derivative vanishes. And it turns out, for studying properties of these recursions, properties of these dynamical systems, those critical points really play a crucial role in understanding more global dynamical behavior. Okay, so the fact that we're looking at 0 is really important, because that is what leads us to understand this set as so much more. So in particular, the boundary, this very fractal-looking boundary of the set, turns out to be what we call a bifurcation locus for this family. So when studying properties of these systems, I won't go into details, I won't define for you the Julia set, but when studying properties of these dynamical systems, we see that the boundary of the Mandelbrot set is really a frontier in many senses. There's a dramatic bifurcation that takes place when looking at the systems for the C values inside the Mandelbrot set versus the C values outside the Mandelbrot set. So these recursions have very different behavior for C inside versus outside. And so one can make this very formal. I'm just giving you a very vague notion that we have a different type of dynamical system. Sorry, so I was referring just to the inside versus the outside, by which I mean interior versus exterior. And the bifurcation locus is then the topological boundary of the set. But the Mandelbrot set itself is closed and includes its boundary. Was that clear what I? OK, great. Yes, so the Mandelbrot set itself is a compact subset of the plane, it includes its boundary. OK, so there, of course, there's more. It's not just a set that we can see in the plane. The set has a lot of structure. I already pointed out, of course, this fractal structure on the boundary. Even the structure of how all of these interior regions become adjacent to one another, how they all fit together, tell us a lot of information about this particular family of dynamical systems. I'll give you a little bit of that as we go. So I like to think of this Mandelbrot set as something like a street map of this family of quadratic polynomials. It, in fact, is telling you all sort of various different possibilities of what kinds of recursions you have and what kind of behavior you have when you start not just with 0, but with any starting point. And another thing I'll mention is that we think of this, one of the reasons that it had become very important is because this same picture will arise over and over again in different contexts, not just in the study of this very particular, very simple-looking family of recursive formulas, but much more generally. So I think of this as universal bifurcation diagram for a very large class of systems. OK, so this is just to give you a hint of why I consider this set important. Let me tell you a little bit of the history. there's a mistake on this slide. So let me just correct it first. This 1978 should be 1979. That's the first published image of the Mandelbrot set by Brooks and Metelsky. As you can see, it's not a very great image, but it's something. They were the first ones to look at it, to plot this particular set. But the first theorem that was proved about this Mandelbrot set, about this set, is that it's a connected, we knew that it was compact, it's a connected subset of the complex plane, which I should add is really not at all obvious certainly from the initial computer images. Here I've generated on my computer, just very crudely, a low resolution image of the Mandelbrot set with a very simple algorithm where you take your pixel and you just check whether after 100 iterates your sequence has gotten larger than 2 or not. And if it has, you color it white, and if it hasn't, you leave the pixel black. So a very, very simple algorithm to draw. And you can see when I do it in low resolution, it just looks like this. This is just a zoom of a piece of the Mandelbrot set. But you see the black with some speckles. Already within a few years, we had much better computer images of the Mandelbrot set. This is an example of one that was published by Mandelbrot himself in 1983. And of course, the set itself is named after him because of the work that he had done on the Mandelbrot set in the early days and his great popularization of this object, which drew a lot of people in to study it. But even in his images, although his algorithms were much better than what Brooks and Metelsky were able to produce earlier on, it's still very difficult to tell what the properties of this set are. But this comment that I made about low resolution and all these black dots, as I said, it's very hard to tell, certainly doesn't look connected from this terrible image that I've produced. But it's actually not a question of resolution, I want to point out, and a lot of people aren't aware of this. Even if I do the same type of algorithm, but in a much higher resolution, and I allow my computer to run for longer and work with, indeed, greater precision, it will still look disconnected. I don't know if you can see with the light on the screen, but those black specks that before just looked like dots, can you see that they've resolved themselves into what look like little baby Mandelbrot sets? So you can see the structure of the dots is much more interesting than just a dot. But it still looks like a lot of dust. It's just that the dust particles look like Mandelbrot sets. So higher resolution will give you something like this. But it still is striking that, again, probably the first theorem about this set is that actually it's connected. Okay? So how do we see that? I mean, the first observation is just numerically, or from an algorithm point of view. There are better algorithms that can help us see more of the structure of this set rather than just a yes-no check. Does my particular sequence get large or does it stay small? If you just rewrite your program, and your computer will do this very, very quickly, to record what we call the escape time. How many steps does it take for your sequence to get outside of a ball of radius 2 instead of just does it exit a ball of radius 2 or not? So if you record how long it takes for your sequence to get big and color according to that time, then you see all of these beautiful images that you find on the internet that I stole at the beginning. So if you just set your computer to record what we call escape time, suddenly all of the beautiful structure of the Mandelbrot set comes out, and it even begins to look connected. Because then you start to realize, there must be something going on in here that joins these little Mandelbrot dust speckles to each other. By the way, the proof so this theorem of Douady and Hubbard, and independently of Sibony from the very early 1980s, the proof is really very simple. It's just an argument in complex analysis. Notice here, these polynomials are holomorphic functions, both of z, the input variable for the recursion, but also in C, the parameter variable. So it's holomorphic. Of course, it's polynomial in both in this case. And so what they do is simply build or construct dynamically a Riemann map, a conformal isomorphism from the complement of the Mandelbrot set to a punctured disk. So topologically, they're the same. Therefore, the complement of the Mandelbrot set is just topologically a punctured disk, so it has to be connected itself. And you use the iteration to build this Riemann map. So it's actually it's a very, very short proof, but certainly required some insight to come up with it in the first place. All right. The next main theorem I wanted to mention, from many years ago, from the early 1980s, was this idea of the Mandelbrot set being universal. Okay, so I alluded to that earlier. I think of this as this universal bifurcation diagram, and that can be made very precise. Now, okay, I've been a little sloppy here. I just want to mention, so this is really an idea of Duhadi and Hubbard, again, in the early 1980s, explicitly that appeared in a publication of 1985. Around shortly after, I think, there's an article of Ekman and Epstein, and there really should have been a ... here and not a comma, because it's not that nobody else was working on this, but I included this article of McMullen from 2000 because it has the title, "The Mandelbrot Set is Universal." So he sort of gathered a lot of these ideas that were out there and anyways, put them into one article and generalized the statement. So what does universality really mean? So this is this concept that explains two different things. One, why do we see the small copies of the Mandelbrot set inside the Mandelbrot set itself? Why do they appear everywhere? But also, why do they appear for other families? And I don't have time to talk about it. There's this whole beautiful theory of it, and related to what we call renormalization, and they introduced this idea of a polynomial-like family. And the idea is that if you take any of these recursions, I gave you a simple one. Input is z, output z squared plus a constant c. But essentially any analytic function defining a recursion of this sort that has this unique critical point. There was something special about that point 0, remember. It was the unique critical point, the only place the derivative vanishes. So when you have another analytic family of such maps with the unique critical point, and it's varying, as long as that critical point is somehow coming back towards itself, exhibits what we call a recurrent behavior, you will see these small Mandelbrot sets when you plot the bifurcation locus. So these pictures of Mandelbrot sets appear over and over again in bifurcation loci of many different families. I have just a couple examples on the next slide to show you just two settings, one of which is very, very famous. And the fact that the Mandelbrot set appears in this particular family of examples actually predates the study of the Mandelbrot set itself, as far as I understand the history. So Newton's method, if you recall, is what we learn in calculus, a method for finding the roots of a polynomial. And we're taught an iterative scheme where if you start with a guess of the root of the polynomial, which is very close to the actual root, then under a certain iterative scheme, it will converge to the root. But for certain polynomials, if you start with a guess, which is not close enough, it might not converge to one of the roots. Other things can happen, and already if you start with a degree 3 polynomial, this iterative method can fail in the sense that most starting points won't converge to a root. And one of the explanations for that is exactly because we see Mandelbrot sets in the bifurcation locus of the corresponding family. If I had a whole hour, I could talk just about this, but I won't talk about just that. I want to talk about other things this hour. This image here, by the way, I just chose. This is one example of a bifurcation locus for a family of, I think this one was just a particular family of rational functions of degree 2. You'll see that this bifurcation locus has lots of features that are Mandelbrot-ish, that sort of resemble in certain ways features of the Mandelbrot set, but there's not an actual Mandelbrot set in this picture, at least not at that scale. But it turns out they have to be there. By this universality, there have to be copies of the Mandelbrot set in the bifurcation locus somewhere, because I know that the critical point is recurrent in this family. And it turns out if you zoom in by a factor of 10,000 for this particular example, you can finally find one. I wasn't able to find one at a scale that wasn't that deep. But I did find one finally for this example at that scale. And you'll see, notice, however, I mean, it's a Mandelbrot set with his head way over to the side. It's a very distorted Mandelbrot set, but it really and truly is, in this case, a homeomorphic copy of the Mandelbrot itself, because we know they have to be there in this universality theorem, or theorems, I should say, and there are many. As I said, there should be a ... before and after the Macmillan name. There's a whole family of results about how these Mandelbrot sets appear and why. Okay. So despite more than 40 years of careful analysis of this Mandelbrot set, there are still many things that we do not know. Some of you may be aware. One of the most fundamental questions about the Mandelbrot set, I've formulated somewhat vaguely here at the top of this slide, in the sense, can we give a complete, say, topological description of this Mandelbrot set? We know a lot about this set. As I said, it's been studied for many, many years, but we still do not have a complete description of, say, all of the connected components of the interior of this set. Let me just show you the next slide before I say anything about the conjecture. We know, so remember, by definition, if I take a C value outside, a parameter outside of the Mandelbrot set, that meant that this sequence, this recursively generated sequence, goes off to infinity. Okay, so out here, outside the Mandelbrot set, it means that this sequence is unbounded. Okay, and it, in fact, will go off to infinity and not return. It turns out for all of the C values inside this cardioid shape, what I've colored here in orange, this sequence will actually converge. It will converge to, it'll have a unique limit point. And for all of the C values in this yellow ball here, the sequence will appear to converge to a cycle of period 2. It will appear to look eventually periodic, bouncing back and forth between 2 values. And for this green bulb over here, it'll appear to bounce back and forth between 4 values, up here bouncing around between 3 values, etc. You can color all various regions according to the behavior of that sequence. And conjecturally, every point C in the interior of this Mandelbrot set will have that same type of behavior. The orbit will converge, the sequence will converge to what looks like a cycle, okay? Conjecturally. And numerically, that is exactly what appears to happen. We've certainly never found any interior regions otherwise, but it is still, in fact, just a conjecture. So the formal conjecture is typically phrased in other language, but was trying to keep it simple, so I'm just formulating it this way. For all C in the interior of the Mandelbrot set, this sequence, this orbit, should converge to something periodic. And this is still an open question. And this question here is really fundamental for our understanding of, as I said, this family is supposed to be universal. This behavior is universal. This convergence to cycles is also universal in the same way. Understanding it here would tell us how, in many, many other contexts. This conjecture I should just mention, which was, I believe, originally formulated by Douady and Hubbard, Adrien Douady and John Hubbard. And the usual way to phrase it in dynamical language is called the density of hyperbolicity. So these examples for C when this happens, or when you're outside the Mandelbrot set, those are examples, those correspond to what we call hyperbolic dynamical systems, which are among one of the easiest classes of dynamical systems. And so we would like that most, in some topological sense, of these systems are easy, are hyperbolic. And we believe that in this particular family, that's actually true. So this would correspond, this is equivalent to saying that most, an open dense set of parameters, corresponds to a hyperbolic dynamical system in this family. Now that kind of behavior is not universal in other families. This is very particular to this type of one-dimensional system. Oh, I guess I should mention, I said we know a lot about the Mandelbrot set. At least modulo this conjecture, we do have a complete understanding combinatorially of the Mandelbrot set. All those colors that I was showing on the previous slide, corresponding to the periods of the cycle to which this orbit would converge, we completely understand the combinatorics, what we call the addresses of the various parameters in this Mandelbrot set. So we do have a very, very good understanding of the Mandelbrot set from a combinatorial point of view. But, as I said, we don't know if there's some region somewhere, maybe very, very small, that doesn't have an address. It doesn't have a number attached to it. That we have not been able to rule out. So I think for me, one of the reasons that this object is so interesting is because it's connected to so many different topics, so many different subjects. Over the years, various mathematicians have brought many, many different ideas to the study of this particular fractal and related objects in different settings. I've listed just a few of the mathematical areas that have been used to analyze the Mandelbrot set and its brothers and sisters. In the early days, so the area of complex dynamical systems really dates back to around 1900. And in the early days, it was mostly analysis. There was some algebra. After all, we're iterating polynomials. And potential theory in complex analysis has played a very important role in our analysis of these types of dynamical systems. But starting in the 1980s, and with the advent of computer graphics and a lot more people interested in the subject, there was a lot more going on and a lot more mathematical tools that have been used. In fact, some of them very, very surprising that there would be connections between these different subjects. And so there were a lot of new tools introduced in the 80s and 90s. And since then, of course, we've continued to develop a lot of these ideas. There's still a lot of these tools being used now and strengthened and generalized in many different ways. But I wanted to say a few words about sort of a different collection of tools that have been used recently in, again, what I consider somewhat surprising ways to analyze this particular family of dynamical systems or recursions and many that are related. And so I mentioned here things that are of a more, going back to this idea of using algebra, the fact that we're iterating a polynomial function, to bring in some tools from algebraic geometry, and especially from number theory, that have taken us even further. So what I want to do, let me see what the time is. OK. So what I want to do with the remainder of the talk is to focus on one example problem, which, to illustrate as just an idea of how we've been able to use some ideas in, well, really coming from number theory, and in fact, especially, I'll mention from, especially, say, I don't know, how should I write this? So the arithmetic or geometry of elliptic curves. By which I mean, of course, tori with a distinguished point because they're groups. So how the arithmetic and geometry of elliptic curves which are things that I'm spending quite a bit of time thinking about in recent years, and they're higher dimensional analogs, a billion varieties, but how the theory and the tools that people have been using for really hundreds of years now to study elliptic curves or abelian varieties and other algebra geometric objects, how we might be able to take some of those ideas and say, oh, well, what can they tell us about the Mandelbrot set? Can they tell us anything about the Mandelbrot set? And then what's been very exciting for me or interesting for me is, well, maybe if they can, maybe then we can go back. And how we can take ideas and dynamics and some information from studying the Mandelbrot set and its boundary as a bifurcation locus, and how that can bring us back. So I put a question mark maybe because it's not clear that you can actually do this. But much of the work that I've been doing in recent years has been trying to build connections between two theories that don't have an obvious connection. And so I want to give you just one recent example, perhaps not the most important example, but in my mind, a fun example, and hopefully to illustrate for you some connection between the subjects. Okay, so all right, one more time. Here's this image that I had generated of the Mandelbrot set with its definition. I just want to make sure everyone's okay with the definition. We have this particular quadratic polynomial, this family of quadratic polynomials. C varies in the complex plane, and the Mandelbrot set is the set of parameters C is this, for which the orbit of 0 under iteration of this polynomial remains bounded. Okay? So it's a compact, connected, fractal-looking subset of the plane. All right. So within this Mandelbrot set, there is a distinguished or important, there's a subset of what I'll call special points. So there's a collection, a countable collection subset of what we consider very special points in this Mandelbrot set. And what are these special points? These are, formally speaking, what are called the post-critically finite polynomials. Okay, that is to say, the Mandelbrot set, of course, was the set of all parameters C where the orbit of 0 is bounded, but inside we have these yellow dots where the orbit of 0 is finite. Of course, if it's finite, it's bounded. So these are in the Mandelbrot set. Okay? So my special points are the parameter C where the orbit of 0 is finite. In other words, of course, it could come right back to itself. Maybe it's actually periodic, returns to 0, or maybe it's pre-periodic and lands on some other cycle. So as an example, the origin is special because under iteration of the map z squared, there's C is 0. You start at 0, you stay at 0 forever. Okay? So I've just put a couple of examples here, well, 4 examples. -1, which is here in my picture, the orbit of 0 is periodic of period 2. Out here at the tip, the leftmost tip of the Mandelbrot set is -2, and that's one of these special parameters because 0 goes to -2, goes to 2, which stays at 2 ever after. And I also just observe I. The point I is, as I mentioned earlier, in the Mandelbrot set, and in fact, it's a special parameter because the orbit of 0 is, again, finite. All right, so these PCF, or special points, are actually very important from a dynamical point of view. Okay? Very important from a dynamical point of view, as they help us understand or classify the possibilities. You might notice from this picture that at least for the interior regions that you can see, there's exactly one yellow dot in each of them. And that is the case for all of these, what we call our hyperbolic components of the Mandelbrot set. So here are just some facts of why these yellow dots are important, why these special points are special. So just a few comments. So let's see. So again, so from the early 80s, again, when people first started exploring the Mandelbrot set, very quickly it was clear that having a finite orbit was important. So as I just said, each of these interior components that you can see will have a unique yellow dot in them. It has what we call a critically periodic center, where the orbit of 0 actually returns to itself. So it's genuinely periodic. Now again, there might be interior components that are not what we call hyperbolic, are not coarse, but do not have a center. Again, I don't know if they exist, but we haven't found any. And it turns out that one can completely classify or fully understand the dynamics or the dynamical possibilities for all of these different regions. They're genuinely different. Again, I haven't talked about the dynamical systems themselves, the global dynamics of one of these polynomials and their Julia sets, but one can give a description of the more general dynamical behavior for any parameter in, say, this region by completely understanding what happens at the center dot, and the dots can be described combinatorially. And this is some work that goes back to the early 1980s. And another thing I want to mention is that I said that the boundary of this Mandelbrot set is a bifurcation locus for this family. It's a set of parameters where bifurcations take place as you vary the parameter. And there's a way to quantify the notion of bifurcation. How much are you bifurcating? There's a natural measure on the boundary of this set. In this case, it turns out to coincide with what's called harmonic measure, as seen from infinity. And it turns out that these yellow dots are uniformly distributed with respect to that measure. This is an observation of Levin, also from the 1980s. That is to say, if you say fix the period of 0, and you let that period grow to infinity, the finitely many yellow dots that you get corresponding to period n, as n grows to infinity, those dots will accumulate everywhere on the boundary. And if you put equal mass on those dots and pass to the limit, you will get this harmonic measure. It also works for the pre-periodic yellow dots, which you cannot see in this picture. They're all on the boundary. And the same for the pre-periodic ones. If you just let the pre-period or period grow to infinity, you will accumulate and converge measure theoretically also to this boundary. Okay, so these, anyways, just to emphasize that these special points are special for several different reasons. Okay. But in recent years, we've understood that they're special for other reasons too. And so just to give you a flavor, on this next slide, some things we've discovered more recently, they also have some arithmetic significance. So a first and very basic observation about these special points is, okay, they're C values which are roots of some polynomial. Okay, this f to the n of 0 is the nth iterate, so it's just the nth point in the sequence. And if you express this with C as a variable, this is just some polynomial, in fact, a monic polynomial in C. And these special points are just the roots of those polynomials with integer coefficients, mind you. These have integer coefficients, and they're monic. So, of course, each such C value is an algebraic integer by definition. And not only that, it turns out it's a set of bounded height. It has some interesting arithmetic properties. We can control the complexity of these solutions. We can control the complexity of these solutions from an arithmetic point of view. When was it? It was in Federico's talk. He mentioned the logarithm of a number. He was talking about the number of digits. He was looking at his polynomials and observing that the number of digits in those coefficients, those integer coefficients, were growing and behaved according to some concavity rule. The log of this number of digits is the log of the number, and that's an example of a height. So in number theory, if you haven't learned about heights, so it's just, if you, for example, for a rational number, the height of a rational number is the number of digits it takes to write it down. That's not the definition we usually give. It's the log of the max of the numerator and the denominator. That's what's called the Weil height of a rational number. And Weil introduced this concept of heights. We extend heights from rational numbers to more general algebraic numbers, again, to reflect some notion of complexity. How difficult is it to write down your number in some sense? And so what I've written here is there are then analogs, dynamical analogs of certain heights, or what we call canonical heights, where you study height growth along orbits when things are defined over the rational numbers or over a number field or in the field of all algebraic numbers, Q bar. And you can try to understand the complexity of these numbers. And it turns out, and this was my point, is that this set of special points is also special from a height point of view. They're all low height, relatively low height. And one can build height functions on the set of all algebraic numbers for which these are precisely the zero height points. And that becomes very useful because we get more information about, for example, about that distribution. I said that these yellow dots are uniformly distributed with respect to some natural measure on the boundary. But it's more than just a uniform distribution. It's a very strong arithmetic uniform distribution. We get that the Galois orbits of these points, if you take any finite set of these points, this set is Galois invariant because it's all of the roots of these polynomials with integer coefficients. But if you take any set, any Galois invariant finite set, and allow its cardinality to grow, you will get uniform distribution to this measure, which it turns out is a much stronger notion of uniform distribution than just taking all of the roots of this polynomial. You just need some Galois invariant subset of roots of this polynomial, and you still get uniform distribution. And that has turned out to have some very powerful applications, not just in this, not in the context necessarily of the Mandelbrot set, but in other settings. And by the way, just a historical remark, if you haven't learned about heights, so this notion, the concept of heights was introduced in the first place to study elliptic curves. And it was really, I guess, in the 20s or 30s, where after Mordell had proved his theorem about finite generation of the rational points in an elliptic curve, they extended that from the elliptic curves defined over Q to elliptic curves defined over number fields. And a key tool for doing so, the fact that the set of rational points is finitely generated, comes from the theory of height functions. And so we in dynamics have sort of imported some of these ideas of going back to Weil and more generally dealing with these sort of arithmetic complexities to try to understand dynamical complexities, that there's some connection between arithmetic complexity and dynamical complexity. And parallels of that sort, I should just mention, now I'm going off on a tangent, really become very broad. Even dynamical complexity in the sense of entropy, or in many different contexts, can sometimes be related to these arithmetic complexities. Okay, let me not get too distracted. What did I want to say? Oh, right. Okay, so one of the questions I wanted to look at, which was, how am I doing on time? Okay, which was a question which was inspired by some results in the world of elliptic curves. Now that we have this distinguished collection of special points, we'd like to understand them, and we'd like to understand if there are some unexpected or expected symmetries or relations among these sets of points, this very special collection of points. So just to make that precise, one way to formulate the question would be, for example, let's look in C2. In other words, say pairs of quadratic polynomials. And the question to be, so do these special parameters obey any unexpected algebraic relations? Can you build polynomial equations, say of 2 variables or of n variables, that these parameters are roots of, that they're solutions to too often or unexpectedly? So here's just one formulation of the question. So we know, for example, if you take 2 pairs, special pairs of my PCF points, of my special points, we know that in the space C2, any 2 points can be joined by a line. We know that from geometry. Any 2 points can be joined by a line. It's true over the reals. It's also true over the complex numbers. And so you can always take 2 such pairs and join them by a line. But is it possible that there could be a 3rd special point unexpectedly on that line? Okay, so here I have my picture of C2. And let's say I have one pair of special parameters and another pair of special parameters. And is it possible that this complex line passing through them just somehow contains 3 more special points? We wouldn't expect that usually. If these were just random points, if there was just some random, throwing down some countable collection of points randomly, you wouldn't expect them to line up too much. You wouldn't expect them to line up too much, and they shouldn't. And if there are too many, there should be some dynamical reason for it. That maybe these parameters, okay, they were arbitrary, but if there's another special point on your line, then the dynamical system associated to this pair, or these two, the two dynamical systems, should somehow be related to the others. Should somehow be related to the others, if you can do that. Okay? So from both a dynamical point of view and an algebraic point of view, we might be interested in understanding what are the symmetries among these parameters, and do we get any relations, unexpected or expected, from them. Okay? Again, just to emphasize one more time, that doesn't look like a straight line. It's a terrible straight line. Anyways, now that I step back and I see it's curved. Okay, again, so just to say one more time that if you were to find an extra point, you have this countable, so inside here, I should emphasize, I'm thinking of this as C cross C. So I have the Mandelbrot set crossed with itself sitting inside. And all of my special points live in this compact subset. Okay, so here's my Mandelbrot cross Mandelbrot. And again, if there were some line or maybe some algebraic curve that had too many special points on it, there's probably a dynamical reason for it. And it would be interesting to understand what unexpected relations you can find between different systems. Okay. I need to rule out some trivialities before assessing a question of that sort. So I just want to emphasize there are certainly some lines that have lots of these special points on them. We could call them special lines. Maybe stupid lines is a better word for it. If you fix one parameter, C, which is special, one of my post-critically finite parameters, and I take, say, the vertical line through it. Remember, this is a complex line. And so there's a sort of a copy of the Mandelbrot set. Well, that was supposed to be a Mandelbrot set. There's a copy of the Mandelbrot set in that complex line. So if one parameter is, say, the x-coordinate persistently, then of course there are infinitely many special points on that vertical slice. Okay, so there are certain lines where you always get infinitely many such pairs. The diagonal line, horizontal lines through one of these special parameters, or vertical lines through one of these special parameters. Okay. But it turns out, and this was a theorem that was proved 6 years ago, or published 6 years ago, which I really like, which states that, well, actually, no, there aren't any algebraic curves that would have, say, too many points except for these special lines. Well, too many in the sense of infinitely many. So this is a sort of starting point. So the very first observation is that if you take any algebraic curve in C2, I'm just working in 2 dimensions for the moment, if you take any algebraic curve, there are only finitely many of these special pairs, these special points on the algebraic curve, as long as it isn't one of these 3 types of special lines. As long as it isn't one of these 3 special lines. And I just want to mention this theorem didn't come out of nowhere. There was a reason they were looking at this very particular question. I said it was an analog, or was a question that came from the study of elliptic curves. And for those of you who are familiar with the theory of elliptic curves, you'll know that the space of all elliptic curves can also be identified, its parameter space, with a copy of C, the usual modular curve, for example, parameterized by its J invariant. So maybe I'll write it this way. It's just as a set of all elliptic curves can be identified with C. And inside it, we also have a set of special parameters. Special in that world would be, say, the elliptic curves with complex multiplication. And I don't have time to go into all the definitions, but some of you may be familiar with some of the theorems. There's a really, one of my favorite theorems, a result of Yves André, published in 1998, which has a nearly identical formulation. And so this theorem was inspired by a particular result of Yves André, which is one of the early results that led to what was then called the André-Oort conjecture, which was just resolved last year or the year before in some work of Pila and Zimmermann and Klingler was not in this final, yeah, no, Klingler had done some of the earlier work, although he was actively involved, and it could be one of the many names. Shankar, I guess, was maybe the third author on the final resolution. But in any case, all right, so many people have been working on problems of this sort, and this one theorem was just, what can we say in this world of quadratic polynomials analogous to what's known in the world of elliptic curves? But I wanted to say, and I'm running short on time as it's now 1:50. Of course, having theorems of that sort are kind of unsatisfying. They don't tell you the answer to, say, this question about lines. If you have 2 points on a line, can you have a third point? I know, what if I don't care about infinitely many? Can you have 6 points, special points on a line, unexpectedly? So it doesn't actually answer that question. And so on the next slide, I just list a few of the theorems of a new project of mine with some co-authors, just to say that actually sorry, one more thing I wanted to say. The proof of this theorem is, by necessity, completely different from André's theorem, the analogous theorem about CM special points in C2. Okay, so André proved almost exactly the same theorem. The special curves are modular curves in that case. The proof is completely different. And in either case, we don't know how many bad points there can be, how many special points there can be on any given curve. But what we do know, in view of actually some recent work that comes from the theory of abelian varieties and elliptic curves, is we do know, for example, that we can give uniform bounds on the number of, say, special points on any given curve. But the bound has to depend, well, by necessity, it has to depend on the degree. We know that a line can pass through, say, at least 2 special points, but typically shouldn't pass through more. I should say, of course, it's still unsatisfactory just to say there's a uniform bound and not know how big that bound can be. And so we've been playing around with trying to get more explicit results in this Mandelbrot case by mixing results from the world of abelian varieties with the dynamical results. One could get a very soft result that a general algebraic curve of degree d will have at most this many points. This is just the same thing as saying, sort of typically a line will only pass through 2 such points. That's still not very helpful. At least in the case of lines, we can go a little further. If you throw out the special lines, it turns out there are only finitely many other lines that have more than those 2 points. By the way, just one more comment I wanted to make. So this uniform bound in this world of CM points on elliptic curves was only established relatively recently, but it's known. The analog of this result is known in the world of special CM elliptic curves. But these results are not known. Were not known, and our proofs actually work in their case also. So rather differently than the earlier work where the proofs had to be totally different. That part of the work applies in both settings. So we get the corresponding results for the world of elliptic curves. So, and I said, but how many? But of course, we still don't know. There are a lot of things that we don't know, and I don't have time to list all those questions. This slide was just to indicate what kind of mathematics we're using. I didn't even say. I just vaguely said from the world of abelian varieties and elliptic curves, but that doesn't tell you what kind of math we're doing. This slide was just to indicate that actually we're really doing a combination of tools from analysis, specifically currents. Currents were the main theme of Camilo's talk this morning. So the analysis is really involves in the complex setting, studying currents on complex manifolds and complex geometry, but combined with techniques from arithmetic geometry. And specifically what we're doing is we're building height functions on certain algebraic varieties defined over number fields. But ultimately, there's some complex dynamics underneath all of this, which is, of course, what we wanted to do, is to say some things about the Mandelbrot set, so you have to use some facts about the Mandelbrot set. And the theorem that we're using about the Mandelbrot set, I wanted to finish by sharing that one of the things that happens is that if you had too many special points on, say, in your family of curves, it forces some unexpected relations, some unexpected self-similarities of the Mandelbrot set. But the Mandelbrot set is not self-similar at all. We call it a fractal, but it is not a self-similar fractal. Even though you see all those copies of the baby Mandelbrot sets everywhere in the boundary, you see lots and lots of copies of the Mandelbrot set, like the pictures that I showed you at the beginning of the talk. Here they are, lots of baby Mandelbrot sets. There are lots and lots of great results. I mentioned Luna's name, who's sitting right here. I wanted to get to this slide, even though I've gone over time. But anyways, there are lots of great results about self-similarity features of the Mandelbrot set. But it's not actually self-similar. So maybe I should just stop here and leave that theorem up there, because I've gone over time. So thank you for your patience.
Thank you very much, Laura, for a beautiful lecture. Questions, comments, please?
What is the bound M of 1? Okay, so that was, what is the largest number of points you can have, special points you can have on a line in C2 when it's not infinite? I do not know. But I'll tell you, actually, it was a question I wanted to pose to all of you, because I think it's something that's amenable to computations and that one can really play around with this. There are 3 lines that pass through the origin that are not special, that have at least 3 points. So just an example. So if you take something like the line y equals I times x. So x and y are my coordinates here in C2. So if I take that line, then I have the special point 0, 0. I have the special point, -1 and -I. And then I have the special point I and -1. Does that work? Y equals I times x. Okay, so I minus I, -1 and 0 are all special parameters. So it's easy to build one line that has 3 points. But that's because the Mandelbrot set has a complex conjugate similarity, and 0 and -1 happen to be in the Mandelbrot set. And so it was possible to build this example because of this complex conjugation symmetry. But I don't know if there are any other special points on this line. And there are only 3 such lines that I could think of last week. And so I'd love to know how many can we get on a given line, and I don't know. Yeah.
Thank you, Laura. More questions? Eduardo.
Yes, so is it known to be polynomial, MD, or?
M of D, is it known to grow polynomially? I have no idea. So really, nothing is known. We only realized a few weeks ago that M of D exists. So this is brand new, which I should say. We were just beginning to take these ideas. There have been a number of really impressive results, not mine, in the world of abelian varieties, getting uniform bounds, control on whether special points of that flavor CM or torsion points. And so we're just beginning to see what they tell us about the Mandelbrot set, but they don't really tell us anything. They're just these general, a bound exists. Yeah, I don't know how it grows with D. I would guess, yes, that it would be polynomial growth. I mean, it's growing at least as fast as the silly bound that corresponds to the dimension of the space of degree D curves. But yeah, I don't know.
George?
So you are posing questions that can be phrased completely in the realm of algebraic number theory, right? Do they make sense? Are they interesting for the global fields of Q?
Oh, yeah. Do the questions make sense when I'm not working over, say, Q, but other, yeah, you mean, and not just number fields. You mean in the setting of certain function fields or certain, yes, a lot of these questions make sense and have been explored working over more general fields. And what's helpful, because I'm working with height functions, indeed, the global nature of the field is really important there. But actually, it turns out that a lot of the theory, some of the things I mentioned on the previous slide with these what are called adelically metrized line bundles actually work in this more general setting of these finitely generated fields. They don't have to be finite extensions of Q, but finitely generated extensions of Q. So then it gives us into the world of function fields that are characteristic 0 also, so that are not technically considered global fields. And so we have the height theory for that as well. And of course, yeah, one could work in characteristic P, but I know nothing about characteristic P, and then the complex techniques don't help. But yes, the reality is that almost all of the types of questions that are explored can be formulated field independently. Yeah.
Carolina?
Yeah, so the question is, what happens if you go from C2 to Cn? And the answer is yes. So let me just go back the answer is yes, you have similar, sorry, I didn't finish the question. Do you have similar results? Yes, okay. Do you have similar results? All right, so just going back here, just the first statement, this result of Gioka, Krieger, Nguyen Yi, so their work only applied in C2. And so actually the first step for uniform bounds was to extend their result to Cn. And it turns out they had all the tools available, but just maybe hadn't done it, or hadn't realized that it could be done. So yes, so this first characterization where finite is replaced with non-Zariski dense. So there's a nicer formulation for higher dimensions, and you can make the same statements, and then yes, all the uniform bounds will carry over. One has to control, say, so one studies, instead of the count of the number of points, one studies the geometry of the Zariski closure of the set of points, and you again get uniform bounds. So actually, all of those theorems can be formulated in arbitrary dimension. Yeah, so it's a very satisfying theory, I have to say, from that point of view. But I don't know any of the answers there either. I mean, in the sense that I don't know any of the explicit bounds.
Daniel?
So in this example where I have three points in the same line, right?
Yes.
In this case, the reason is the complex conjugation, and you see some similarity between the Julia sets in this corresponding point. So in the other examples that you have, you see some similarity in the Julia sets in the corresponding parameter?
Well, as I said, I only know 3 such lines. And they're like y equals ix, y equals minus ix, and maybe y equals minus x. I mean, they're all silly like this. And so the same types of points create the symmetries. And so, yes, we get that Julia set symmetry. But I think it would be very interesting to know that truly, if there were a line that happened to have 6 points, would that mean that there was some... That could, a priori, mean, yes, that there's some connection between the Julia sets. But those Julia sets shouldn't have any relations. So we should be able to say, if there were too many points on a given line, it would force a dynamical relation that cannot exist. And therefore, that M of 1, who asked, right? That the maximum number of points I should get should just be 3. Maybe those are the only exceptions. And actually, it's uniform in a very clean way. So I would boldly conjecture that that it might force some actual dynamical relation, which cannot exist. That's a lot of what happens in many of these settings, is that it's a little easier to see with infinitely many special points, but even just having too many special points should still force some unexpected symmetries. Yeah.
In the last theorem of Law, is the open set, is any open set?
Any open set, yes.
Because we know that the Mandelbrot set is self-singular at the Mesuriewicz.
Okay, so it's a different, yeah, so in fact it's exploiting some aspect of what happens at the Mesuriewicz points. Whoops, oh, I had a bunch of open questions at the end that I'll tell you about if you're interested later. Sorry, so the theorem says, right, so if I take any open set that intersects the boundary and some conformal isomorphism to any other open set that intersects the boundary, if it actually takes the boundary to the boundary, it had to have been the identity. So the point is that the Mandelbrot set, as I said, so it has copies of the baby Mandelbrot set, but it's really not self-similar at all, because so what you see when you zoom in near any point in the boundary of the Mandelbrot set is what looks like the Julia set of the corresponding dynamical system. As you mentioned, the Mesuriewicz points, that if you zoom in at one of the Mesuriewicz points, so one of my special points that happen to be in the boundary, if you zoom in there, you'll see that Julia set close up. You'll see that Julia set. But what we know is that for distinct values of C, those Julia sets will not look the same. They can have a complex conjugate symmetry, like I and minus I, for example, but the Julia sets are forced to be different. So we can pin down information about where we are in the Mandelbrot set by knowing what the corresponding Julia set looks like. And those things are different. And that's how this proof goes. It says 2021. This was, in some sense, a statement that was known to the experts for many, many years, but no one had ever really written it down or figured out quite how to write it down. And Yushang Luo, this is the result. It was maybe one of his first projects as a graduate student, worked this out. He was a student of Kurt Macmillan, so he's my mathematical brother. And I really like this result. And his proof also, because it uses exactly what happens near those Mesuriewicz points, the special points. All right, I guess we should stop.
Okay, I don't see any hands anymore, so let us thank the speaker again.